So starting the recording of today's technical sessions, I'm going to make, so I have made two trees. That's perfect time to compare the models. I have made two trees on several trees, and now I want to compare, use a node to clearly compare the two based on the same metric. So how do I do? First of all, if you want to compare, when you compare, you use the node in assess. There's a node called model comparison, right? So you drag it and connects every model that you want to compare with to the model comparison node. If that model comparison node is correctly specified, after you run it, it will give you a report of which model is the best, right? But make sure that you specify the metric correctly as the one that you need. So before you run it, take a look at the model selection. Selection data is default. Typically, it should, if you have data partition, it should use the validation. If you want to make sure, explicitly, or I guess, yeah, that's it. For selection metric, if the question asks for the best decision tree, then you select the decision. Decision here is a misclassification. Right? And that selection table, make sure it's validation. So this has to be validation. And selection statistic has to be the one that you want to use. And after that, you're ready to run. So open the results of the model comparison and look at this table, basically. And it has many columns. Every column is a possible metric that you can compare the models. Few of them is what you are looking for. So be very careful and look at the table. Based on the selection in the property, the best model is indicated by a sign on the first column. To confirm that, what we're looking for is the validation set and misclassification rate, the lowest, right? And it's typically on the left side. Selection criteria: valid means validation set, misclassification rate. The best one is the one above, is the tree 2. Tree 2 has the name of best decision tree. So the best decision tree is better than the maximal tree, which is frozen, obviously. But the results confirm the expectation. It's not different by a big margin, It's only that different. Does that answer the question, Bao?
Yeah. So you said misclassification. The higher the number,
the higher the number, the worse the model. Any other question for homework and decision tree in general? Great. Good timing for a break. We'll take a break of 10. We'll come back 33.
quick question.
Let me pause the video. So resuming the hands-on session, we are going to train a few regression models, but before that we will do an imputation to deal with the missing values. So On the tutorial, it has trained 2 trees. We have 2 trees. I have 2 trees, but the 2 trees are not exactly the same. I have a maximal tree. It doesn't have. But assuming that's you can do it. You can do the probability tree by modifying the assessment property, and then you can train a probability tree. That's fine. We'll ignore it for now, and you can afterwards you can put it together. So we'll just start a new path, and we'll take a look at the missing values. So here we're going to the train set. Wait, so highlight that, and the data partition. We'll go to the exported data. We'll look at the train and browse the data set. And a few variables have a fairly significant amount of missing values. The income, I think that's the one. Median income. Age. Where is my age? Gift amount. You already see missing values. And there are different. Well, there's a special point to make about missing values. You really have to understand what the attribute means when you think about the missing values. Sometimes you expect there are missing values, but there are not. There are no missing values in some of the attributes. You should be doubtful about the data set. Let's see here. Gift amount, average card is the card that they fill out. Gift amount, average card, 36 months. During the past 36 months, 3 years, average donation amount of this household made. It's more than reasonable to have a subset of data, customers that have never donated, and that's why you have missing values for those households. If you have values in those cells, that is not reasonable, right? So what does it require for you to go to this point? You have to understand the business. You have to understand the context, the project, and and where the project, which stage is the project. If it's already past data preparation stage, and you're in the modeling stage, but you see no missing values in this variable, you should pause and and evaluate and go back and check the previous stages. So all of these require care. And as for the point of demo, we're going to use the imputation of SAS. But we're only going to impute for certain variables, because for some others, for the one that I just pointed out, it doesn't make sense to impute those missing values. They are intended to be missing values, right? So let's see. So use an impute should be under modify. Right below the trees. Everybody's following along? Great. Okay, there are some properties to change. So this is a one action takes care of all, hopefully. So it's a sort of a a mode and try to fit the mode to different kinds of variables. So, and because there are variables that we do not want to be imputed, so we should exclude some of the variables from this operation. I think this is what's different that I will do from the tutorial. So I'll go to variables. And so we have everything. We have everything input except the target. Gift average 36. So for all those gift average, I should have not used the default imputation. And that should be good for now. And then I will modify the default setting to apply the imputation. The tutorial says it's okay to use, for class variable, it's okay to use the count, which is basically the mode of the categorical variable. And for interval variable, it's okay to use mean of that interval variable. Well, neither is good enough for us. As you did in the homework 2, for interval variables, an obvious better option is what's better than mean? The median. Who's that median? Yeah, median. Because median is less sensitive to outliers, and given enough data, and in almost all the situations, median and mean are almost closely enough, and median is less sensitive to outliers. So under interval variable, the default input method would be the median, and we leave the default target none. Well, for this course, we never impute the target. The target is the one to predict, not for impute. For class variable, we would like to use something more intelligent. We would like to use a mini scale decision tree to implement the imputation rather than go directly with the same fixed value for all the values under the same variable. So we would like to use the tree surrogate, which is a mini scale tree that supposedly should replace a different missing value, a different value for the missing value based on the other inputs. So after the 3 operations, after you have selected no for some of the variables, and after you have changed the default methods for 2 types of variables, now you can run it. Oh, I think there's one more thing to change, the indicator, right? For indicator variable, the tutorial says unique, and then change the role as input. So these are a group of actions that has a purpose. So what does the indicator variable mean? Indicator variable is an additional variable created based on the status of missingness of a particular role, right? Input the indicator of missing, so let's call it missing indicator. Missing indicator is going to be 0 for a particular row if it doesn't have any missing. Right? If it's all has values, there's no missing for the row, the indicator is going to be 0, so no missing. If it's going to be 1 based on the other options that you select, here we use unique. That means a separate missing indicator is created for any variable, input variable that we have to impute. Right? Let's say age. There is missing values in age. We imputed age. Right? Then there is a missing age indicator created for those rows that have missing age imputed. So why do we need this? Because in data pre-processing, you learn that sometimes missing values are not random, and the missing status may tell you something besides the fact that besides the value that you imputed. Sometimes you impute with some value, it's not perfect. The status that is missing may tell you something. Most of those situations are related to sensitive data or something like that. So the sensitivity of that of that variable may tell you something about the target. We just don't know. A lot of times you don't know precisely what the conclusion is. Does it really matter? Then why not keep it? Why not keep the indicator and let the data tell you, let the model results tell you if it's important or not. So selecting unique will create one missing indicator for every variable that has missing imputed. And change row from reject input simply includes those indicator variables in the next step. Include them as an input for whatever model is connected after the impute. So it's going to show up in the exported data as an input variable or as input variables. We can check that by going to the exported data. So this time I don't browse because it's a large table. I look at the properties and I look at the variables. Wait, I haven't run it yet, I think. I have to run it again. And you can look at the results of imputation and see that only age is in the report. That means only age is being imputed. So one indicator variable will be created for age indicator, and the original variable name is demographic age. It's using median to impute, and the variable as a result is put into a new column, which is the imputed variable imputed demographic age, and then the original variable is rejected because every useful information has been retained in the new column. And we also have an indicator, which is M, missing indicator of the dem age. Then we can go to the exported data to look at row. So imp dem age is the imputed values with the original values if they are not missing. And we have an M indicator. Both of them have input row. The indicator has a binary level. which is as expected. So as a result of imputation,
The column that then age is gone.
it's gone from this view. It's there in the data set, but it's not going to be effective in the next step. Right? I think if you browse it, you can still see it. You still have, yeah. No, that's not the one. It should be the dem age.
Or just I think that's because that's the label of it.
Yeah.
That's a label. Good point. Yeah, good point. This is a level. This is a label, but previously, that's a variable name. Right. Okay. So now we can proceed to just running a simple regression. Under model, typically. Now connect that and wait for a moment. So I'll just run it without changing anything. Everybody's here?
So question, the SAS don't have, because if you look at the different methods to impute data, which one is best for which situation? Like,
For
what is like history? Like I was just looking at the different options, like distribution, what's different between tree and distribution?
I know all of the when I know the best practice for our purpose, we have the best scenario in class variable using the tree surrogate. That would be the unambiguous best assumption to choose. For the interval, it's not always very clear the distribution. There's some opaqueness there, and it's hard to search online for the exact answer. It's a long list. It's a big. I experimented with the different trees method, but it doesn't produce, the right one for me. For interval variables, when I use a tree, it should not have produced a decimal for what should be a natural target variable. So it doesn't make sense. So then I tend to use medium. It's the safe one. The safe one. Okay, let's go into the results. Okay, so for because we left some variables out of the imputation, then those rows with the missing values in those columns, the average gift amount, those variables that have missing values, the rows will be left out. So we're working with a slightly smaller data set. Just be conscious about that. So by default, you have four windows. That is not the overfitting graph. So don't don't panic. It shouldn't go that way. It's not. It's not a cumulative. It's a lift chart, basically. And we talked about that in almost the last chapter of supervised methods. We'll talk about different metrics of comparing models, of using more realistic decision making rather than simply look at misclassification rates and the mean square error. There are different ways to look at the evaluation. Here, it's fit statistics. It just calculates all the different metrics to compare models. You have misclassification rate, you have error, mean square error, and you have all the others, likelihood, you have ICC, things like that. The fact number is comparing the different coefficients of the regression model. Why there are so many? I think we only have 20 or something variables. Why are there more than like 50 bars? Each bar is for a coefficient of the regression. If you're familiar, or at least know, sort of what the coefficient is about, right? It's the coefficient of the regression equation, right? That's associated with a particular input variable. Why there are so many bars? While we only have this many inputs. This is not this is a outside the box thinking to sort of to fully understand a regression. These are relevant questions, but not part of the requirement. It requires some experience with the regression. So
Is there one for each level target?
right on. Yeah. When you have a no, not target, sorry. Input.
Okay.
Input. The coefficients are not for target. Target doesn't have a coefficient. Target is not an input. Target is the left-hand side. Y hat. On the right-hand side, you have many terms, right? You have each term, you have a summation of different terms. Each term is a multiplication between the coefficient and the input variable. But if you have a categorical variable, you obviously don't have a value for the levels. They have to arbitrarily create dummy variables for each level and leave one out. You don't have to fully understand it, but if you understand, you know what I'm saying. Then it increases the number of coefficients by how many levels that you have in those categorical variables. So that's why there are this many bars. For the churn example, the example that you have worked on several homeworks, the state variable, if you include it as input, the state variable has 51 levels. And so if you include that in regression, it will have 51 minus 1, 50 levels, dummy variables created for each of the unique levels, leave one out. So that's why you have so many bars.
So it turns each level into a binary.
Yes. That's how you can numerically model it in the regression. So that is actually how regression is different from decision tree, right? In decision tree, those unique levels, they are taken care of by split rules. It's natural to decision tree. For regression, it's not natural. So you have to have a workaround to have this many, and the solution is not perfect, but at least it's feasible. So it's crossing the two models and sort of compare them outside the box. And this, if you look at the length of the report, this mighty table, this mighty window, is probably the most useful, at least for the homework and for this course. It has probably 500 rows with many, many results. So you have to know where you look at. So I'm not going to talk about the entirety of the table. For the regression, we want to look at some goodness of fit metrics, and this is a multiple regression of a regular kind. There's no selection going on here, so it just trains one model, and then we want to look at the final results. So there's a search, fortunately there's a search function for SAS, and typically you look for the unique label that is close enough to the part of results that you need to look at. Analysis of variance is the convenient one. It's not there. It's missed typo. Let's see. Analysis of effects. So there's only one, and fortunately, that's close enough to where we want to look at. And the section above that is a overall model fit statistic of log likelihood. And let's see. And for this is a logistic regression. The target variable is 1 or 0, right? It's a binary target, so it's a logistic regression. There's no R squared because it's logistic regression. There's a pseudo R squared, but barely useful here. So it's going to be slightly different from the homework. But what I'm going to talk about is almost similar. The analysis of maximum likelihood effect estimates. If you search for this label, it's quicker. It's more on a target. Here, this shows you a complete list of coefficients for this logistic regression. Every row is for a different target, different input variable, or a unique level of an input variable, except for the first row. First row is intercept. If you know what it means, an intercept is the y average. And it has a coefficient. Typically, we just want to make sure there is an intercept, and that's it. For everything else, it's the coefficients. And for every coefficient, there is a standard error calculated. There is a t at the chi-square test of the significance of that coefficient, and there's a p-value associated with the chi-square. And there's another column specifically for logistic regression to interpret the results. For now, I'll skip it. So to do the homework, this is the section that you need in order to extract the coefficient to put the equation together. Right? This is the part. And for homework, there are only 2 variables. So it's going to be 3 rows or 2 rows, depending on the question. Right after chi-square.
Like TR.
Right. This is not. It's not calculating because we're not asking for it. That's the exponential of the estimate. Estimate is this. So this is the parameter estimate. This is taking the exponential of that parameter, which gives you the log odds of one unit change of that input to the outcome of the target. beyond the requirement. But it gives you a nice way to interpret what it really means in the logistic regression framework. So you compare it with 1. If it's greater than 1, then you know that if this variable becomes larger, the log odds of the person being a donor increases. So you compare this with 1. You compare this with 0. So it's sort of corresponding with each other. If the coefficient is below 0, the log odds should be below 1 because it's taking the exponential. Does that answer the question?
And you're looking at maximum likelihood estimates?
Say that again.
This is the analysis of maximum likelihood estimates?
Yeah. So in other words, it's the analysis of coefficients, regression coefficients. Right. Let's do another regression. So this is the plain regression. We didn't do anything, so it uses the default setting. What that means is for every input variable that is not rejected from the importing data source, it's going to use those inputs that are not rejected, including the imputed variable and transformed variable. No transform. Imputed variable and the dummy variable, the flag variable for imputation. So it uses all of those as an input and puts everything into a big regression model and calculates the result. If you don't see that specific result for analysis of maximum likelihood estimates, that means the model did not converge. So there's a problem with computing the coefficients. And that's a serious problem for that. We rarely run into that for using the model, using the data set that we use. Okay, the next one, optimizing, selecting inputs. Okay, so for regression, it's different from decision trees. One is that the way it includes nominal variables is different that I talked about. It creates flag variables. It creates flag variables to incorporate the different classes. Sort of treating those different levels of the nominal input as if they are independent. So that's not perfect, right? For a person in the sort of middle income range, is going to have a dummy flag variable for mid income range as 1 and high income range as 0. That's the way you put the flag variables for categorical. In regression, the two variables independently work as if they are two separate variables, but they really come from the same variable, right? So this is beyond the requirement. I'm kind of speaking the language that if you know, you know what I'm talking about. If you don't know, you don't have to know. Anyway, that's one difference. The other difference is in terms of managing the complexity. So think about how decision trees manage the complexity of model in terms of how big the tree is. It has a built-in pruning process, and it's a exhaustive search, right? It searches for the best one, and although the computation is intense, it seems to be manageable. But the result is something that you don't have to worry too much about, our, is the complexity of the model managed well? Is the final optimal model sort of hampered by the complexity of the tree? It's not. Because it really searches all the possibilities and come up with the best one with the highest validation performance, right? And you don't have to point your fingers to which variable is more important. Now you can do that when you train it. You can interactively intervene and say, now I want this tree to be this. But when a model prunes the tree, it goes with the exhaustive search. It covers every corner, right? So you exerted some influence in training the tree, and in the pruning process, it searches for all the possibilities, and in the end, ends up with the best tree based on the metric. So minimal intervention required. For regression, it's a different story. Whatever variables that you include, it will run and run the same model. It will not automatically remove or select for you. And it gives you a coefficient estimate. And you need to interpret the coefficient estimate. And it's not as straightforward. You can do hypothesis testing. But that testing result depends on what other variables you include in the regression. So that's the tricky part of regression. Different combinations of inputs give you different results. So that's another difference. That's why there's a different selection process created for regression. The basic term of that framework is the stepwise. You can go forward, you can go backward, and you can go backward, forward, sort of iterated process, which is a comprehensive stepwise. The book has the more specifics. I'm not going to just talk about it. It's kind of hard to demonstrate the process unless I scroll thousands of lines of results to show you what really is changing between the steps. And it's not this part is not as critical. So what we'll do is do a stepwise and to see if it's different from the default regression tree that we trained. So another regression model this time, let's see, model selection. Model selection by default is no. So there's no selection process. For this one, we're going to change it to stepwise. And there are specific criterions that you can configure under the stepwise regression. We'll run the basic stepwise regression for now. And I'll rename the node to reflect the change. Wait. Is that the one that the tutorial asked for? Yeah. Question?
Stepwise was the only change you made, right?
Yeah, the name. No. Under in the property, I changed model selection from no to stepwise, and that's the only thing.
Okay.
And one thing that you notice immediately is the number of columns is reduced. So instead of including everything allocated, it does have a selection process. It stops at a certain point based on the rule of stepwise regression, right? So that's the immediate notice. And the reason that is reflected is because working with regression, the most important mechanism of handling overfitting and trying to improve the model process is trying to focus the model more on the informative attributes. Now, what does an informative attribute mean? Meaning the input variable that supposedly carries the most important predictive information about the target. That's the informative target. There are only this many informative targets there if you include them. If you include those, then any additional one is going to have some overlap with the ones that you already included, and the marginal increase of the model is going to decrease very quickly. Beyond a certain point, you're going to hit the overfitting, definitely. So that's why stepwise manages the process of focusing on the important attributes. Now, instead of decision tree, every time it considers all and then select the best. Here, it doesn't have that. So then increase the results, and this time this window is much longer. It's 1,000 lines, just because there are different steps. It's stepwise, The stepwise combines forward and backward selection, and forward and backward selection are the two different options that you have for model selection. The forward means it includes variable one by one. So, but only include those that meet some criteria. It first tries to include everyone, not everyone, each one individually, and then compare the p-value. The lowest p-value is the variable that's retained and included in the model. As long as the p-value is below some threshold that you specify. So the process goes on. It keeps including variables that has the lowest p of the remaining variables, as long as the p is below some threshold, until the point that there's no candidate to be included, the model will stop. So that's a forward selection. The backward selection is exactly backward. Include everything first, and then run the giant model, compare the p-value, and eliminate the variable with the highest p, because the highest p-value is the lowest significance of the variable. They keep going until there's nothing else insignificant to be eliminated, and the model stops. And then stepwise is combining the forward and backward together. Every time, start with the forward, and then after the forward, do one time of the backward, and then resume with the forward, and then do one time of the backward until there's no point to change. So that's basically it. If you search, wait. If you search analysis of maximum likelihood, wait, Corfit, yeah. You have multiple, right? If you search analysis of maximum likelihood estimates, you have many such tables, and you see a difference. If I go back up, you see the table is shorter until the point there's only one intercept. If I go down, and this is the final model, it shows at the bottom. Wait, if I go up, the first model only has intercept. Second model has one more variable. Third has two more. The fourth and fifth, and goes on. The regression model gets bigger, but there are subtle changes in the input variables included because it's a stepwise. It goes back and forth. And the last one is the final one. But here, the final one doesn't mean it has the best misclassification rate. It doesn't. It simply is the stopping point of the stepwise. Right? There's nowhere to go, and it stops. So you will have to have another mechanism to compare the model in terms of the performances on validation. Everything down here is on the training set. That makes sense? So consider it only the splitting process of a decision tree. It doesn't have the pruning exactly down here, but there is a little bit of complexity management here by eliminating those input variables that seem not to be informative by going the stepwise process. So here, the final model has, other than the intercept, has 1, 2, 3, 4, 5, 6, 7 inputs. One of the input is a categorical input. It has 6 different levels, 5 dummy variables included as an intercept, and that's it. That's a final model. If you compare, if you use the model comparison node to compare this regression, stepwise regression, with a decision tree, then model comparison will use this final model to compare with the other trees that you compare with. Now, back to the conceptual. Default regression tree. Assuming that I have trained 3 trees based on the donation data set. I have a best decision tree. I've already trained it. Best probability tree. I haven't trained it, but you can imagine. And a default regression, which is all the variables included. And the regression tree has it's one regression tree. Has all the variables. It has a validation misclassification of 43%. Mean square error of 0.24. So if you compare with the best decision tree on misclassification rate, on the train set, the regression tree performs better because it includes all the variables. It tries to beat hard on the training set and try to maximize the amount of variances explained by the variables. But if you compare the validation, it performs poor because it's overfitted. It uses all the variables. If you compare if you compare the mean square error of the regression with that, regression also wins. But the validation performance also suffers than the best probability tree. This is bigger, even though it's by a small margin. So working with regression requires more care. The decision tree takes care of things very easily for you. You know, here or here, we didn't do much to train the trees. You know, the tree is selected and exhaustive search in the background is done for you. For regression, if you simply move a regression and run it, typically it's going to be overfitting.
So will the train always be better for regression than the decision tree, and the validation will always be a little bit worse? Or is that just for this example?
Let me understand it exactly. Are you comparing the models?
Yeah, just like how
Or-
you had mentioned that the train for regression for misclassification is slightly better than train for the best decision tree, and then you showed how the validation is a little bit worse, and how it's the same when looking at the MSE.
Mm-hmm. Let me see how to answer that best. First, the train of regression not always better than the train of trees. Not always. And it goes the other way. Validation of trees not always better than validation performance of regression. Depends on how you train the regression. This regression is overfitting. If it's overfitting, then you can expect that. You know, if you have a best decision tree and then you have an overfitted regression, then that should be expected. The training performance is typically better in the overfitted regression, but the out of sample performance is worse because it's overfit, right? Because of that question, I think of another. If you compare within the same model, not cross model, within the same model, you typically expect training to be better than validation, right? If it's because we select the model based on overfitting graph, and the overfitting graph typically goes that the validation performance is worse than the training performance because model tend to overfit, right? It fits better on the training set on which the model is training. So if you see it's across the board for the same model, same metric, training is better than validation in terms of error. Right. So the stepwise is what I train the second regression, right? And forward backward selection is as I explained. Stepwise combines the two and do an iterative alternation of the two processes. If you compare stepwise regression with the default, which is overfitted and includes every variable in it, and if you compare the stepwise regression with the best tree, what will the result be? The overfitted default regression and the stepwise regression train performance is worse because it's not overfit. Validation performance is better than the default tree, overfit tree. And same thing goes with the mean square error. That make sense? And if we compare the stepwise with the decision probability, stepwise outperforms the decision tree. So the mechanism of regression is good, but just requires you to know more and be careful about training. Stepwise regression is better across the board. this here it tends to say train a large number of regression models, train more regression models, and select the best. It's not a large regression model. So for under under the stepwise regression, as well as the forward and backward selection, you also have something similar to the subtree assessment plot, which is the stepwise model comparison. And let me show you. Under this stepwise regression, same way that you will look for. It's by different name. It's iteration plot is the different middle steps of the selected process of the regression model, and you compare the model performance on the validation metric.
So for this, you pick the last data point, or how do you pick?
It shouldn't. It should pick. So I think there is. Wait, no. Okay, there's multiple things going on here, because the target is binary. Right. It by default it chooses misclassification rate, and but validation set misclassification rate as the default metric. We didn't change the default. We only changed the stepwise. So by default by default, this graph only shows the lines under every square error. That's not the matrix that the model is selected. Otherwise, it should have selected this point, right? So if you change it to misclassification, that should look better. Nah. Okay, so some step in the middle that the selection metric is not what we want, and we can go back and fix it. So if we look at the selection criteria, the default is something that is sort of opaque, and if we choose misclassification, but under the validation set, and rerun the model, look at the results. It should be much better right now. So the selected model has the best validation set misclassification rate. And something bizarre here, if you notice, at the very early stage of this graph, you have the validation set error rate even lower than the training set validation metric. That is not typically happening. In this data set, it's fake, to be honest. It's a case, so with a little bit less of care, it's not mimicking the reality. But typically, that's not the reality. And even the best model has better performance on the validation set.
So if you want to use instead of risk classification, the average
Mean square error.
then you would select the validation error.
Exactly. Yeah. Make sure it's valid. It's validation.
Yeah.
Yeah. But I think even if I chose the misclassification rate, it maybe also works for every square error, because a lot of times it's the same model. For regression, it's different. So every step here, it's the same model. But for decision tree, it might not be the same model. right? Because we see that best probability tree and best decision tree are different, even though they have the same number of leaf nodes. For regression, it's exactly the same. There's no exhaustive search here. That puts us to the right time to finish. So that's it for now. I'll see you in 2 weeks. Enjoy the break. Let me know if you have any questions. And you should expect to see the video maybe within 2 days in Blackboard.